Alright, so here we are still in chapter 11.2, and we're looking at the three different types of intermolecular forces that we're going to learn about right now. The first is called dispersion forces, or sometimes known as London dispersion forces, or sometimes just known as London forces. And these are ones that happen at one instant in time, and then the next instant they might change. And they all have to do with the number of electrons that something has and how those electrons are currently in a particular state around an atom. So here, for example, is a neon atom, and it has 8 valence electrons. But at one instant in time, perhaps the neon atom has all 8 of its electrons over here on this side. And if all 8 electrons end up over here on this side, it sets up a momentary or instantaneous dipole. Dipole meaning that there's a more positive charge right here and a more negative charge right here. And then maybe at that same instant in time, another neon atom has the same thing going on. So another neon atom has all the electrons kind of over on this side of the atom. Well, that sets up a dipole in this atom as well, and now there's an attractive force between these two. This attractive force between these two atoms at one instant in time is called a dispersion force, or a London dispersion force. Now the next instant in time, this attractive force that's labeled right here might not exist because the electrons might move somewhere else, and then they're not polarized that way anymore, and then they don't stick together as good. That's why the number of electrons really makes a difference, because if something has more electrons, it's more polarizable, and therefore it can have more London dispersion forces. So the more electrons something has, the more electrons a species has, the more possibly polarizable it is, and the stronger the London dispersion forces will be. Now, shape can also make a difference in a molecule. So for example, on this page we can look at a linear molecule of pentane, and we can look at it's kind of a hot dog shape right here and has a fairly large surface area as compared to the same molecule, C5H12, but in more of a spherical arrangement, and so it has a smaller surface area. And surface area makes a big difference in the polarizability of those molecules, because the more surface area that you have, the more opportunity it has for electrons to build up or not build up in a certain part of the molecule, and then they can attract better. That's why you can see the boiling point of this N-pentane is 309 versus the boiling point of this neopentane or spherical pentane being 282. Why is this one less? Because there's less surface area for those electrons to build up around and then attract to another one. So number one thing in dispersion forces is more electrons. The more electrons you have, the stronger the dispersion forces. The second thing, if they have the same number of electrons, now look at the shape of the molecule. And remember, the more surface area you can get, the stronger or the better they'll stick together. The second type of intermolecular force are called dipole forces. And dipole forces happen between polar molecules. And polar molecules, remember, are ones that have a dipole moment that's set up inside of them. So you need to draw the Lewis electron shape for that, and then you have to notice that the shape is asymmetrical. When it's asymmetrical, then we know that it will be a polar molecule, and the molecules will stick together by a dipole force. So here's an example of two molecules. I'll give you a second to draw them down. These are CH3CN molecules, and you can see when I draw the Lewis dot structure of this one that it is asymmetrical. There's a nitrogen over here with an unshared pair of electrons, and then there's a really nice symmetrical CH3 on here. But overall throughout the molecule, it's a polar molecule, and we can draw a dipole moment going this way, saying it's more positive over here and more negative over here by this nitrogen, because obviously nitrogen's much more electronegative than the other atoms inside the molecule. Now I have the same molecule drawn right down here. I'll give you a second to write that molecule down as well. And you'll notice in this molecule I also put a plus right here and a minus right here. That's because it too has a dipole moment, or a more positive area right here and a more negative area right here in the molecule. And so these would stick together by a dipole connecting to a dipole, and those would be attracted by that intermolecular force. This force is usually a little bit stronger than London dispersion forces, but of course it depends on the number of electrons that something has as well. In this case, the dipole-dipole force would be the main one that would be holding those molecules together. The last type of intermolecular force, here are some examples of dipole-dipole forces that I think I showed you in a previous video, where you can see a dipole in this molecule, dipole in this molecule, and then they stick together. The last intermolecular force is one called hydrogen bonding. Hydrogen bonding. And I'm just going to move this page over and we'll bring up the hydrogen bonding or hydrogen forces page. Some books call them hydrogen forces. Many of them call them hydrogen bonds. And people usually get confused when you say hydrogen bonds because they think it's a hydrogen bonded to something else. Well, this is not the hydrogen bond. The hydrogen bond is actually the molecule sticking together with another molecule. And so hydrogen bonds are a special kind of dipole-dipole force, and they happen when an H, a hydrogen, is connected to an FO or N, an F, an O, or an N inside of a molecule. And so here we have an H connected to an O. Obviously, is there a dipole moment set up inside of this molecule because it's a polar molecule. Water molecules are polar. And then we have an attraction between the hydrogen part right here that has a very exposed nucleus and the oxygen part right here that's very negative. This attraction right here is stronger than a regular dipole-dipole force. So these bonds right here between the H and the O are covalent bonds, and they have bond energy of like 450 kilojoules. The hydrogen bond that holds one molecule to another is not very strong at all. That hydrogen bond is maybe like 15 kilojoules or so per mole. And so it's a lot less than 450. And so when you change phases of matter, of water, you don't break these bonds right in here. You actually break the hydrogen forces in between the H of one atom and of one molecule and the O of another molecule, another water molecule. You can see right here in your textbook they show the hydrogen bond as little dots right here. In hydrogen fluoride they show it really nicely right here as well. Notice how it's between two molecules. Notice how they show it in ammonia right here, and then they show it between ammonia and water here as well, and then they show it between water and ammonia again in just a different way. So, hydrogen bonds occur when there's a hydrogen bonded to an FO or N, a phone or a NOF, an FO or N inside of the molecule. Well, why does it have to be an FO or N? It's because these are super electronegative atoms. And when an H is connected to one of those super strong electronegative atoms, it has its electron pulled really close to the N or F, exposing the positive nucleus of the hydrogen, and then allowing that hydrogen to be really, really attracted to something that is very negative, like the nitrogen part on ammonia, like the fluorine part of the hydrogen fluoride, like the O part of the water. So that's an overview of the three intermolecular forces that we're really focused on during this chapter. In the next video, we'll look at lots of questions that have to do with identifying the type of forces, whether it's dispersion, dipole-dipole, hydrogen forces, and how they affect physical properties of melting point, boiling point, sublimation, etc.